have the latitude, the longitude, and we're going to use JavaScript to read this in this where.html file. It's going to actually read this right there and pull that data in, and that's how we're going to visualize. I'm not going to go into great detail on how the visualization happens, but that's what's happening, and so we're going to write that. So we're going to actually write this to a file. So let's go ahead and run this code and say Python 3 geodump. Okay, so it wrote 120 records to where.js. So if we look at where.js, this is now the new data that I just downloaded moments ago. And it says open where.html in a browser. Now this will, you'll need the Google Maps API, and you might not be able to see this depending on where you're at, but here you go with Google Maps locations, and I think if you hover over this, you can see, and you see the UTF, why we there in that particular thing, why we had to use the UTF-8 when we wrote the file, so that we didn't end up with trouble writing the file out. And so there you go. And so that is a simple visualization, and just a simple visualization. It wrote this where.js. If you are smart with HTML and JavaScript, you can look at this where.html file. It's really just reading through a bunch of data and putting the points. That's all there is, but I'm not going to go through that. So, at least not in this. And so I hope that this was useful to you, and thanks for watching. So now we're going to write a search engine, do some of the things. We're going to do PageRank, and we're going to visualize it in a web browser and show the weights. We're really only going to do PageRank on one page because you want to have links that more than one page that points to a page, so that you can figure out which pages are more or less important. And then we'll visualize it. And we'll run the PageRank algorithm, and we'll separately do all this. So at this point, we're going to do pretty much the web crawling, the index building, and the searching. We're not going to really search it. We're going to visualize the index. But you could write a simple program to do searches for keywords and figure out which page was the most likely page for a keyword. And that would be a fun additional thing to do. So the web crawler is this program that hits a page, pulls down the HTML, parses the page, looks for links, makes a queue of incoming links that are as yet unretrieved, and I'm going to do this in a simple SQLite database. And starts out with, the database basically starts with one link as the starting point, and then it retrieves that page, and then you see the database end up with lots of unretrieved pages, and then it goes back in and picks a random page and retrieves that one, and then it just expands and expands. This code that I've built that you're going to play with only stays on one website, otherwise it would go crazy. But of course Google doesn't use an SQLite database running on your hard drive. But you'll get the idea. You'll see this thing exponentially gain links, and you'll run it for a while, pull down 1,000 web pages or whatever. But of course, make sure that you don't violate any terms and conditions. And again, I've got some data sources that you can use, and they're not rate limited, but you can also use things like Wikipedia, which I think they sort of discourage you, or drchuck.com, which has no rate limit, or who knows what, right? So just be careful. Don't do this on Facebook, and don't do it on Google. Don't get yourself in trouble. And if you're using, you know, a internet connection where you're paying for bandwidth, be careful. So this is the idea of the web crawler, and this isn't my picture. This is the classic picture of a web crawler. Read a page, parse it, take all the URLs and stick them in a queue, grab again and again. So for us, this scheduler is going to do it as long as you'd say, oh, do 100 pages, or it runs until it blows up. I mean, and again, these processes that have the network in the loop, it's really important that they behave well when they blow up. And that's why databases are so useful, because you can be writing along to the database and some random thing happens and blows your data up, and you start over. So you're reading these things, you're storing each page, building up your storage, etc., etc. So you just keep on doing that. And with this program, you'll be able to retrieve some stuff, then run the PageRank, then you can retrieve them more, and then you can run some more PageRank, and you can kind of see how Google sort of evolves its index over time. Of course, we're so much simpler. And like I said, be careful when you crawl. You're going to run a crawler that just goes as fast as it can. But Google doesn't do that. It's careful not to overwhelm any websites. It's trying to be smart about the use of your bandwidth on your website. There is a file. RCode won't bother looking at this. But there's a file called robots.txt that real web crawlers look at, and it gives a list of the things you are allowed to look at and not allowed to look at. And so if you go to Google and you see a search that says, we're not allowed to show you the summary text of this page because of the robots.txt, it's there, and you can go and you can actually see a robots.txt. Like on, just go to any website, it's at the top root, blah, 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 /robots.txt. It's not a path. It's not slash this, slash that, slash something else robots. It's at the very, very top of a website. The index building uses the PageRank algorithm. And the whole goal of the PageRank algorithm is to figure out which pages have the most best links. So having the most links is really easy. You can just say how many links go to this. But the problem is you got to figure out the value of those links. And then you have to, how do you figure the value of those links? By looking at how many good links come to it. So it turns out that it's an infinite problem. It's an infinitely difficult problem to use PageRank. But you can approximate it, and what happens is after a while it converges to a reasonable value. And so we're going to run the search index, and each time it runs, you're going to see that it says, you know, how much did these numbers change? And what happens is, in the beginning, they change very wildly, but quickly they flatten out. And it has the best way to think about the PageRank is think about how water runs, where you have a small little stream going by a house, and sometimes it rains, sometimes it's dry, and sometimes, you know, and there's like a little lake, and the stream is always running, and it doesn't go up and it doesn't go down. It might go up a little bit if it rains a lot, but in general there's sort of a steady state, meaning that whatever water's coming in is about the same as the water going out. So we think about this in terms of web pages. The value of the links coming in is roughly the same as the value of links going out. So when that starts to balance the in and the out value from each of the nodes, then you've got pretty stable. And so what Google does is they have a really relatively stable assessment of goodness and value of pages, and they use that to compute PageRank. And then they throw a few more pages in, and it kind of has to adjust for a while, but it reconverges. And so this is a calculation that generally converges, and it doesn't vary wildly. And that's why Google's pretty good at kind of arriving at the true value of something. So let's take a look at what we're going to do in this application. Again, we have a file that is going to spider the web, and we only have one database. Again, in this one, we'll have two databases in the next one. And so this is spider is the restartable part, and what we actually do is we put one URL in, the starting URL, and then spider walks in and asks, are there any unretrieved pages? And it does that randomly. It sort of picks among the unretrieved pages and says, okay, great, I'll go retrieve that page, and then I'll parse that page, and then I'll put in a bunch of new unretrieved pages, okay, as well as the text of that page, and then a bunch of unretrieved pages. And then it'll go back up and it'll say, oh, give me one of the randomly non-retrieved pages, and it'll grab a next page and pull that page down and then add to it. And so this is like, there's a page and then a to-do list. And then this one becomes a page and then adds a few more things to the to-do list. And so the to-do list, or the unretrieved URLs, grows very rapidly. And the retrieved ones grow sort of as you retrieve them one at a time. But you've always got this long list. If you have a really short site that only has like 2 links, if you start at drchuck.com/page1.htm, it'll go to page 2 and then go back to page 1 and it'll be out of things. It'll have retrieved all of the pages. And so if you have a website that has no external links or has very few pages and they point to each other, this will run out of things to do. But if you go to a page like my blog or the code that the sample stuff that I have up for you to spider for testing on drchuck.net, it'll run for a very long time, and you'll have far more pages to retrieve than pages that you retrieve. But that's okay. At some point, you can stop this. Maybe it stops because you ran out of bandwidth, or maybe your computer went down, or who knows what, right? but it's okay. This is a restartable process because it always has some pages that are retrieved and some unretrieved pages. You start it back up, it picks randomly from the unretrieved pages. Your database is the sort of persistent state of your spider rather than a bunch of dictionaries or lists inside the Python, which go away when the program dies. And so at some point you have, let's just say, a few hundred pages in here and a few thousand unretrieved pages. You can run the PageRank algorithm. And what the PageRank algorithm does is it loops through all the pages and figure out which pages are linked to which pages, and then reads the numbers and then updates the numbers, and then does that some number of times. And so this is where the numbers, all the pages sort of start out with goodness of 1. I think this printout is showing that goodness of 1, and then it changes, and then the goodness goes to, some of the goodness goes up to 2, some of the goes to 7, and whatever, but then it does this over and over, and then it uses these numbers, and then they change again. And so there's a number of time steps that this PageRank runs, and you will see as the PageRank runs, when I show you the code, you'll see the average sort of change in these numbers across all these things, and you'll see that the average goes down very rapidly as you get through. And so usually with a few hundred or even thousand pages, like 100 plus times running this algorithm, and these numbers have converged. And that's when you sort of can begin to trust the numbers. Now there's this one program called SP Reset, which sets all the pages back to 1, so you can start this over. So if you were to spider for a while, run SP Rank for a while, play around, and then you wanted to spider some more and start it over, you could say, oh, let's start the PageRank completely over. Or you could simply take the new pages and watch it adapt. Either way, this is just a way to reset all the pages to have sort of their initial value of a goodness of 1.0. So at some point you run this. This part here runs really slow. This part runs super fast, like in the blink of an eye. This one is pretty fast. And then at some point you've got these pages that have, numbers on them. They have values on the pages. And there's a couple of programs that allow us to visualize that. One is the dump, which just reads it and checks to see. It shows the new PageRank, the old PageRank, and various other things, and shows just a way to dump it. And then there's this thing that reads the whole thing. You say, I'd like to do 25 of the best. It sorts it by PageRank, and then produces a JavaScript file that has just the numbers in it. And then there is some HTML and a visualization library called d3.js, which you can read about, that when the HTML starts, it reads this and has this nice force-directed layout of the PageRank. And you can hover over things and you can see what PageRank you've got. And so that is the PageRank algorithm that we're going to do. And up next we'll do the largest and most complex of these things, and that is the email. We're going to spider some email, which is about 1 gigabyte of data. Okay? We're doing a bit of code walkthrough, and if you want to, you can get to the sample code and download it all so that you can walk through the code yourself. What we're walking through today is the PageRank code. And so the PageRank code, let me get the picture of the PageRank code up here. Here's the picture of the PageRank code. And so the PageRank code has 4 chunks of code that are going to, 5 chunks of code that are going to run. The first one we're going to look at is the spidering code, and then we'll do a separate look at these other guys later. So the first one we'll look at is spidering. And again, it's sort of the same pattern of we've got some stuff on the web, in this case web pages. We're going to have a database that sort of just captures the stuff. It's not really trying to be particularly intelligent, but it is going to parse these with Beautiful Soup and add things to the database, okay? And so then we'll talk about how we run the PageRank algorithm and then how we visualize the PageRank algorithm in a bit. Now, the first thing to notice is that I've got to put, I put the Beautiful Soup code in right here, okay? So this is, you can get this from the bs4.zip file. There might be a README, no, but there's a README somewhere. But you got to use Beautiful Soup, you got to put this bs4 zip, or you have to install Beautiful Soup for your stuff. So I provide this bs4.zip as a quick and dirty way if you can't install something for all of the Python users on your system. So that's what it's supposed to look like. You're supposed to have it unzipped right here in these files, and I don't know what dammit.py means. That came from Beautiful Soup. If you look, it's in their source code. So I'm not swearing. It's Beautiful Soup people are swearing. I'm sorry. I apologize. Okay, so the code we're going to play with the most is, in this first one, is called spider.py. And, we're going to do databases, we're going to read URLs, and we're going to parse them with Beautiful Soup. Okay? And so what we're going to do is we're going to make a file. Again, this will make spider.sqlite. And here we are in PageRank, and else minus L. Spider.sqlite is not there, so it's going to create the database. We do create table if not exists. We're going to have an integer primary key because we're going to do foreign keys here. We're going to have a URL, and the URL which is unique, the HTML which is unique, whether we got an error. And then for the second half, when we start doing PageRank, we're going to have old rank and new rank, because the way PageRank works is it takes the old rank, computes the new rank, and then replaces the new rank with the old rank, and then does it over and over again. And then we're going to have a many-to-many table, which points really back. So I call this from ID and to ID. We did this with some of the Twitter stuff. And then this webs is just in case I have more than one web, but that really doesn't make much difference. Okay, so what we're going to do is we're going to select ID URL from pages where HTML is null. This is our indicator that a page has not yet been retrieved. And error is null, ordered by random. And so this is our way, this long bit of stuff. And not all this SQL is completely standard, but this order by random is really quite nice in SQLite. Limit once is just randomly pick a record in this database where this true is true, and then pick it randomly. And then we're going to fetch a row. And if that row is none, right, we're going to ask for a new web, a starting URL, and this is going to fire things up, and we're going to insert this new URL. Otherwise, we're going to restart. We have a row to start with, and otherwise, we're going to sort of prime this by inserting the URL we start with, and insert into it. If you enter, it just goes to drchuck.com, which is a fine place to start. And then what we do is what this does is its PageRank is it uses this webs table to limit the links. It only does links to the sites that you tell it to do links. And probably the best for your PageRank is to stick with one site. Otherwise, you will just never find the same site again if you let this wander the web aimlessly. And so I generally run with one web, this should be probably called websites. And I pull in all the data, and I read this in, and I just make myself a list of the URL, the legit URLs, and you'll see how we use that. And the webs is what are the legit places we're going to go? Because we're going to go through a loop, ask for how many pages, and we're going to look for a null page. Again, we're using that random, order by random, limit 1. And then we're going to have we're going to grab one. We're going to get the from ID, which is the page we're linking from, and then the URL. Otherwise, there's no one retrieved. And so the from ID is when we start adding links to our page links, we got to know the page we started with. And that's the primary key. We'll see how that primary key is set in a second. So otherwise, we have none. And we're going to print this from ID, the from ID and the URL that we're working with. Just to make sure, we're going to wipe out all of the links. Because it's unretrieved, we're going to wipe out from the links. The links is the connection table that connects from pages back to pages, and so we're going to wipe out. So we're going to go grab this URL. We're going to read it. We're not decoding it because we're using Beautiful Soup, which compensates for the UTF-8, and so we can ask. This is the HTML error code. And we checked that 200 is a good error. And if we get a bad error, we're going to say this, error on page. We're going to set that error. We're going to update pages. That way we don't retrieve it ever again. We basically check to see if the content type is text HTML. Remember, in HTTP, you get the content type. We only want to look for the links on HTML pages. And so we wipe that guy out. If we get a JPEG or something like that, we're not going to retrieve JPEG. and then we commit and continue. And so these are kind of like, oh, those were pages we didn't want to mess with. And then we print out how many characters we got and parse it. And we do this whole thing in a try except block because a lot of things can go wrong here. It's a bit of a long try except block. Keyboard interrupt, that's what happens if I hit Control C at my keyboard or Control Z on Windows. Some other exception probably means Beautiful Soup blew up or something else blew up, and so we indicate with the error equals -1 for that URL so we don't retrieve it again. At this point, at line 103, we have got the HTML for that URL, and so we're going to insert it in, and we're going to set the page rank to 1. So the way PageRank works is it gives all the pages some normal value, and then it alters that. We'll see that in a bit. So it sets it in with 1. We're going to insert or ignore. That's just in case this pages is already the pages is not there, but and then we're going to do an update, and that's kind of doing the same thing twice, just sort of doubly making sure if it's already there, this or ignore will cause this to do nothing, and the update will cause us to retain it, and then we commit it so that if we do selects later, we get that information. Now this code is similar. Remember, we use Beautiful Soup to pull out all the anchor tags. We have a for loop. We pull out the href, and you'll see this code's a little more complex than some of the earlier stuff because it has to deal with the real nastiness or imperfection of the web. And so we're going to use URL parse, which is actually part of the URL lib code. And that's going to break the URL into pieces. Come back. We use URL parse. We have the scheme, which is HTTP or HTTPS. If it's this solves relative references. This solves relative references by taking the current URL and hooking it up. URL join knows about slashes and all those other things. We check to see if there's an anchor, the pound sign at the end of a URL, and we throw everything past, including the anchor, away. If we have a JPEG or a PNG or a GIF, we're going to skip it. We don't want to bother with that. We're looking through links now. We're looking at all the links. And if we have a slash at the end, we're going to chop off the slash by saying -1. And so this is just kind of nasty choppage and throwing away the URLs that we're going through a page and we have a bunch that we don't like or we have to clean them up or whatever. And now, and we've made them absolute by doing this. It's an absolute URL. This is just, you write this slowly but surely when your code blows up and you start it over and start it over and start it over. Then what we do is we check to see through all the webs. Remember, those were the URLs that we're willing to stay with, and usually it's just one. If this would link off the sites of the sites we're interested in, we're going to skip it. We are not interested in links that leave the site. So this is like link that left the site. Skip it. But now we finally, here at page line 132, we are ready to put this into pages, the URL and the HTML, and it's all good, right? And that one's going to be null right there because we haven't retrieved the HTML. This is null because this is a page we're going to retrieve. We're giving it a page rank of 1, and we're giving it no HTML, and that way it'll be retrieved. And then we commit that, okay? And then we want to get the ID, so we could have done this with one way or another, but we're going to do a select to say, hey, what was the ID that either was already there or was just created, and we grab that with a fetch 1 and say retrieve to ID, and now we're going to put a link in, insert or ignore into links from ID to ID, which is the ID, the primary key of the page that we're going through and looking for links. To ID is the link that we just created, and away we run. So it's going to go and go and go and go. Let's go look at the create statement up here. From ID and to ID right there. Okay, so let's run it. Python 3 spider Python. So it's fresh, and so it wants a URL with which to start. And I'll just start with my favorite website, www.drchuck.com. Now this basically, this first one you put in, it's going to stay on this website for a while, okay? So I'll hit enter, and let's just grab let's grab one page, just for yucks. Okay, so it grabbed that, and it printed out that it got 45 characters, and it printed out that it got 6 links. So if I go to this and open database, and I go to code 3, and I go to PageRank, and I look at this, let me get out so it closes. So here, so notice this SQLite journal. That means it's not done closing. So I'm going to get out of this by pressing enter. And so you'll notice now that that journal file went away. Otherwise, we would not be getting the final data. There we go. Okay, so Webs, let's take a look at the data. Webs has just one URL. That's the URLs that we're allowing ourselves to look at. You can put more than one in here if you want, but most people will just leave this at one. Pages, so we got this first one, and we retrieved this, and this is the HTML of it, and we found 6 other URLs in there that are drchuck.com URLs, right? There was lots of other URLs in there, but there were only 5 other ones that we found, okay? And so, and what we'll find is if we go to links, we'll see that page 1 links to 2, links to 3, links to 4, links to 5, links to 6, because the links is just a many-to-many table. So page 1 points to page 2, page 1 points to page 2, page 1 to 3, page 1 to 5, okay? So that's what happens when we have the first page. So let's retrieve one more page. Now, we could have started a new crawl, but it's gonna stay on drchuck.com, and I'll just ask for one more page. And so now it went and grabbed. It randomly picked among these null guys, and I'm gonna hit enter to close it, and then I'll refresh this. And so it looks like we retrieved OBI sample, and we didn't get any new links. And so the links page, no, we didn't get any new links. So that page, whatever that was, OBI sample, had no external links. So let's do another one. One more page. So that one had 15 links. So let's take a look now. So now we have 15 pages. It picked this one to do, right? And now it added 15 more pages. And then if you look at links, you will see that page 4, which is one it just retrieved, links back to page 1. So now we're seeing this is where the PageRank is going to be cool. 4 links to 1, 4 links to is whatever, away we go, right? 1 goes to 4, 4 goes to 1. I should have probably put a uniqueness constraint on that. It's not supposed to duplicated that. Okay, so let's run this a bunch of times now. So let's just run it 100 times for 100 pages. It'll take a minute. So you'll see it's like freaking out on certain pages and not parsing them. You know, it's found its way into my blog. It's finding like 27 links. This table is growing wildly at this point. It's going to take us a while before we get to 100. It's kind of slow. Now the interesting thing is I can hit Control-C at any point in time. Right? And so that blew up. But it's okay because the data is still there. And so if we go back to pages, for example, and we refresh our data, we see we got a ton of stuff. And this will restart and all the things. So if we search this, that I sorted that by HTML, you see that there's lots of files that we've got, and it's never going to retrieve those again because those have HTML. So then I can run this thing again and start it up. And when I say Control-C, your computer might go down, your network might go down. There's all kinds of things that might happen, and you just pick up where it leaves off. It just picks up where it leaves off, and that's what's nice about this. Okay, so that's pretty much how this works. we've got this part running. We're seeing it flow into Spider.SQLite. We're seeing that we can start this and replace this. And so what I'll do is I will come back in the next video and show you how all these things work together and then how we actually do the page rank. So thanks again for listening, and see you in the next video. We're picking up in the middle here where we are running a simple Spider that's retrieving data and putting it into running this spider.py file, and it's cruising around and doing things. And the beauty of any of these Spider processes is I can stop anytime and just hit Control-C. And so we take a look at the spider.sqlite file and retrieve it, and it looks like we got 302 pages. I don't know how many we got retrieved. 70. Okay, there we go. We got about 100. Oh wait, I'm looking for the wrong thing. No. Yeah, we got about 107 pages. So what we're going to do now with 107 pages is we are going to run the PageRank algorithm. Okay, so let's take a look at that code. So the idea of PageRank, we're going to run this PageRank algorithm. The SP reset just resets the PageRank, and SP rank runs as many iterations of PageRank. So the basic idea is that if you were to look at the links here, you know, we think of page 1 pointing to page 2 gives some of page 1's love to page 2. Page 4 has some value that it gives to page 1. You go on, and page 2 gives love to page 46, over and over and over again. And so, but the problem is that how good is page 1, and how much positive karma does it give to page 2? And so what happens is we start by giving every page a rank of 1. We say, look, everybody starts out equal. But then what we do is we divide up in one iteration of the PageRank algorithm, we divide up the goodness of a page across its outbound links, and then accumulate that, and that becomes the next rank. Okay, and so let's take a look at the code for the PageRank algorithm. So this is pretty simple. It only imports SQLite 3 because it's really doing everything in the database, right? It's going to be updating these columns right here in the database. And so so we're going to do some things here to speed this up. This rank runs, if you're thinking of Google, this rank runs slowly and is going to run continuously to keep updating these things. So the first thing I do is I read in all of the from IDs from the links. Select distinct throws out any duplicates. And so I have all the from IDs, which are all the pages that have links to other pages, because all the pages are in pages, but in links to have a from ID, you have to also have a to ID. Okay, and so we're also going to look at the pages that receive PageRank, and we're kind of pre-caching this stuff. Okay, and so we're going to do a select distinct of from ID and to ID, and loop through that group of things. And we're making a links list here, and so we're saying if the from ID is the same as the to ID, we're not interested. If the from ID is not already in my from IDs that I've got, I'm going to skip it. If the to ID is not in the from ID, meaning that this is a to ID that's not also, we don't want links that point off to nowhere or point to pages that we haven't retrieved yet, and that's what this is saying. So this is really going to give us, it's a filter on the from IDs and the to IDs from the links table, so that it only are the links that point to another page we've already retrieved. And then we're going to keep track of the entire superset of the to IDs, the destination IDs. And I'm just putting these all in lists so that I don't have to hit the database so hard. Okay, so this is getting what's called the strongly connected component, meaning that any of these IDs, there is a path from every ID to every other ID eventually. So that's called the strongly connected component in graph theory. Then what we're going to do is we're going to grab the we're going to select new rank from pages where for all the from IDs, right? And so we're going to have a dictionary that's based on the ID, the primary key, that's what node is, equals the rank. And so if we look at our database, that means that for the part of the strongly connected component in links, we're going to grab this number and stick it into a dictionary based on the primary key of this, based on the primary key, this number right here. So we're going to have a dictionary that's this mapped to that. Again, we want to do this as fast as possible. Now we're only doing one iteration at the beginning, so it asks how many times you want to run it. Okay, so we just make an integer of that. We check to see if there's any values in there. If there are no values, we are bad. And now we're going to go I equals 1 to range many. This is going to be 1 to 1, so it might run however many times. And then what it's going to do is it's going to compute the new page ranks, and so what it's really going to do is it's going to take the page rank, the previous ranks, and loop through them, and this is the previous ranks is the mapping of primary key to old page rank. Okay, and for each node, we're going to have total equals total plus old rank, and then we're going to set the next ranks to be 0. Okay. And then what we're going to do is figure out the number of outbound links for each page rank item. So node and old rank in the list of the previous ranks. These are the IDs we're going to give it to. And so for this particular node, we're going to have the outbound links, and we're going to go through the links and not link to itself, although we made sure that doesn't happen. We make sure that this, but then we're going to make a list called give IDs, which are the IDs that node is going to share its goodness. And now what we're going to do is we're going to say how much goodness are we going to flow outbound based on our previous rank of this particular node and the number of outbound links we have. So that's how many that's how much we're going to give in our outbound links. And then what we're doing is all the IDs we're giving it to, we started with the next ranks being 0 for these folks. These are the receiving end, and we're going to add the amount of page rank to each one. So whatever this is, so we'll go through all of the links, give out fractional bits of our current goodness, and it's accumulated in each one, and so eventually all the incoming links will have granted each new link value. Okay. Now I'm just going to run through and calculate the new total, and this is this evaporation. The idea is that you can't. It has to do with the PageRank algorithm that there are dysfunctional shapes in which PageRank can be trapped, and this evaporation is taking a fraction away from everyone and giving it back to everybody else. And so we add this evaporative factor, and then we're going to do some computations just to show some stuff, and that is we're calculating the difference, the average difference between the page ranks, and you'll see this when I start running it, and that is telling us, this is going to tell us the stability of the page rank. So from one iteration to the next, the more it changes, the least stable it is, and you'll see in a sec that these things stabilize. And then we'd say, what's the average difference in the page ranks per node, which is what this is, and that's what we're going to print. And now we're going to take the new ranks and make them the old ranks, and then run the loop again. So I'm not actually updating the database each time through the PageRank iteration, but then at the very end, I am going to do the update for all of these things and update all of the rankings with a new rank. So I'm doing an in-memory calculation so that this loop here runs screamingly fast. Even if I want to do like this loop 100 times or 1,000 times, it's really all just in-memory data structures. Okay, so it's probably easier just for me to show you this. It'll be very, the code runs quite simply. Python 3 sprank rank.py. And so I'm only going to run it for one iteration, and that means that it's going to, this loop here is just going to run one time. And so it's going to start with the page ranks of the new rank of 1, and it's going to just run one iteration and put the rank there, okay? And then update this as well. So let's go ahead and run that once for one iteration. Okay, and so it ran one iteration, and the average change between the previous rank and the new rank is 1. So there, it's actually quite crazy. So I'm going to refresh here, and you'll see that the old rank was 1, and the new rank went way down, way down, way down, way down, down a little bit, down, down some, up a whole bunch, down, down, up. So you see that they went down and up. Now the sum of all of these numbers is going to be the same, right? Because all it did was like floated out and recalculated it. And so that's what happens with PageRank. And so what will happen is if I run one more PageRank iteration, these numbers will be used to compute the new rank, and then these will be calculated to the old rank. And so you'll see that these will change again. So I'll just run it one more time. So I'm going to run one iteration, and then I'm going to hit refresh. So you see all these numbers got copied over, but now there's a new rank that's computed based on these guys. And so they're getting, this one went up. This was 0.13. That's gone up a little bit. This one's gone up some more. This one's gone up. This one went down, right? So this one went down from 6 to 8. And you can see that the difference is now the average difference between this number and this number across all of them went from 1 point something to 0.41. And you'll see that with these very few pages, this PageRank converges really quickly, okay? So let's run it again. And I'll just run 10, and you will watch how this converges. Okay, so there you go. It converges. So, and you're seeing now after like 12 iterations that the difference between the old rank and the new rank, well, that's because it's that old rank. I'll run one more iteration so that you can see. So this old rank is less than, 0.005, and so now you can see that these numbers are sort of stabilizing. This is the average, that 005 number is the average difference between these two things. Now, if we're going to pretend to be Google for a moment, we can say Python 3 spider.py. So let's just do 10 more pages. Now what's going to happen here is these new pages are going to have page ranks of 1. Okay? So let's get out. So if I do a refresh now and I look at new rank, so there's these guys that have high rank. What you'll see, I hope, yeah, okay. So you see new pages, right? These are the new ones that we just retrieved. I don't know if they're linked or not, and they all got 1. So some old pages are way up, 14. Some pages, if we go downwards, are way down, right? So these are like useless pages. They point to somewhere, but nobody points to them. That's what happens with these page ranks, okay? So what happens is the new records get this 0.1, and so if I run the ranking code again, and I run, let's just run 5 iterations, you'll see that the average delta goes up just briefly as it sort of assimilates these new pages, and then it goes right back down again. And so that's what's happening with Google. It's sort of running the spider to get more pages, then running the page rank, which gets disturbed a little bit, but then it reconverges very rapidly. And of course, they've got billions of pages, and we've got hundreds of pages, but you get the idea. Okay, and so I can run page rank like 100 times, and after a while, it just sort of hardly is changing. So that's 2.7 to the negative 10th power. So now, let me run it one more time to update the stuff. And if I refresh this, you're going to see, look at how stable these numbers are. 14, 9, 4, 3, 5, 9, 1, 5, 6, 7. The difference is there in the 7th one. So that's why this whole PageRank is really cool. It seems like it's really chaotic when it first starts out, and away you go. Okay? So that was just this, SP rank, right? SP rank, and SP reset, we can look at that code. I won't bother running it. It just sets the old rank to 1. That's it. That's as much code as you got. It just restarts it and lets it rerun. So I'm going to stop now, and I'm going to start a new video where I talk about this phase here, where we're actually going to visualize the PageRanked data. And what we are in the middle of is we're in the middle of the PageRank code, and we just got done running the PageRank, and so we have spidered the code, we've run PageRank a bunch of times. SP reset allows us to restart the PageRank algorithm if we want, but we're not going to play with that. We're just going to play with SP dump and SP JSON and do the visualization, which is the fun part. So I'll go into SP dump. So this is simple code because it's really just running a SQL query and then printing stuff out, right? So we connect to our database, create a cursor, and then just do a select count, and we're going to just show the number of links. We're going to order by the number of inbound links descending, so we see the most linked things, and we'll see the top 50 of that. So this is just a sample. You'll tend to write little helpers like this that make your life easier, just to show you the kinds of things that you want. spdump.py, and like you just kind of test to make sure that's like, oh, this looks right to me, you know. And so here is the number of inbound links. So that's my blog that has the most inbound links, followed by my uncategorized, whatever that is. And these are the number of inbound links within my own blog somehow. I don't know, because this is not looking at the whole whole internet at all. So there we go. So that's SP dump, pretty straightforward. And now we're going to go through the visualization process. And so this is going to look at all that data and produce some file, a JavaScript file. It's going to write a JavaScript file that will then be fed into my visualization using D3. And SP.json is going to do a big long join. It joins the links with the thing, and where HTML is not null and error is not null. You know, order by the number of inbound links. So we're looking at the things that have the highest number of inbound links. We're going to read all this stuff. We're going to read through all those rows and pull out the page rank for each one. We are looking for the highest and lowest rank, because these numbers can vary quite widely. They go all the way from, you know, 0.000 to 20 or 30. And so it asks how many do you want to do, so it only does the top like 20 or something, and you'll see why we need that in the visualization. And so this is just checking. And so we're going to write out a file. We'll see what the format of this is. It's just a it's just a JavaScript file, and we're going to write out. We're basically normalizing the rank. We're subtracting the minimum rank, and because we're going to turn this into line weight, the thickness of the line, and so we're dividing by, you know, we're normalizing the rank to be the thickness of the line and the size of the ball. You'll see all this, and so this is really just writing some JavaScript with the little strings and stuff like that, and then we're going to finish the JavaScript, and then we're going to write all the links out. So these are the balls that you'll see. And this is showing what this is, drawing all the lines, and this is again normalizing things for thickness and printing these things out. Now I don't want to go through this in tremendous detail, but so I'll do Python spjson.py. Let's do the top 20 nodes, and if I take a look at this file spider.js, you can see that it's some objects that basically put the page rank in, which ID it is, and that's a way for me to be able to link back and forth. Weight is how big the little circle is, and then I have the links. And I only asked for the top 20, right? And then this is the thickness of the line, where the line starts, where the line ends, okay? So this is read by this HTML file, and it's going to read somewhere this force.js file, and my own spider.js code. This is some JavaScript. No, the force.js is the visualization code, and this is D3, the visualization library. So I'm using this D3.js, which is a really great visualization library, and this is just drawing the circles and making the circles colors and making the circles bigger and smaller, and then connecting all the lines in between it. So this is just there. This data feeds that thing, and so when we're all done, you simply say open. You don't have to do anything. Open force.html. And so all this beautiful JavaScript stuff is like, oh wow, that's really cool because you can move these things around. Whoa! You can see the circles are bigger. If you hover over it for a while, it shows you the big ones. You can see these things, and it's kind of cool. So I gave you all this force.js and force.html, and so that kind of visualizes the PageRank, and you could use this to visualize quite a bit of stuff. It'll take you a while to pull down enough data from a real website, but after you pull down 400 or 500 pages, if you have some time, and then the visualization is quite interesting. But you can see why we had to pull down several hundred pages just to get this much PageRank information. Okay, so that gives you a sense of how to run the PageRank code in Python for everybody. So thanks for listening. The last visualization application that we're going to take a look at is mailing lists, and that's kind of ironic. We started with the mailing lists, and we're going to end with the mailing lists. The mailing lists, of course, are from my open source Sakai project, which I love and very proud of. And so what we're going to do is we're going to crawl the archive of a mailing list, and then we're going to do two visualizations. One is a activity visualization, and another is a word cloud. So it's probably the more important thing is when I do the demonstration of how the software works. So this is a large data set, so you got to be careful. This could spider gmain.org, which is a very free and friendly archive. This data originally came from gmain.org, but I've got a copy of it. And so gmain.org is not rate limited, but if everyone who is watching this starts spidering gmain.org at the same time, you will crash it. It just doesn't have the horsepower to give you this data as fast. And so I've got something that can give you the data super fast and has no rate limit on a really good server, and it's cached all around the world using a technology called Cloudflare. So please, please, please don't point this at gmain.org. Point this at the URL here, mboxdrchuck.net, etc., and then you can run this as fast as you like. Now, another thing to worry about is if you have a metered connection. So don't do this on a cell phone connection because you'll pay thousands of dollars perhaps. Make sure you run a no-cost connection before you start running this, because this is going to pull a lot of data down. If you just start this from scratch and you let it run, it on a super fast connection, downloading the whole thing is probably about 4 hours. On my home connection, when I had like about a 10 megabit connection, it took several days. And so just understand that in this one, it's both fun to deal with a ton of data, and it's scary to deal with a ton of data. So this one is big. This one is, you'll see the process in action because it'll run for a while. The things will take a long time. So here's basically the flow of the data in this particular one. You are going to have the restartable spider that talks to the API, mboxdrchuck.net, which has a scalable copy of all this information. And again, it's going to do kind of a raw database. Not a very clean database. It's sort of a mess. It's just enough columns to keep track of whether or not we've got this page or not. And so this has, the ones we've retrieved so far. And so what Gmain does is it sort of scans down to see where to retrieve next, gets that, and then starts scanning and then adding things here. So it just adds it, and then it blows up. And then it comes in again and says, okay, I'll start here, and then it starts retrieving stuff and fills this in, fills this in, fills this in. And sometimes you put like a delay in this so you don't overwhelm networks or don't overwhelm servers. But basically this is pretty much a raw retrieval of the email messages. And this file can get rather large. This is the one that's greater than a gigabyte. Now this data is actually really nasty. It's email data. The date format's changed. This is data that lasted from 2004 to like 2012 or 13. And so this data is got a lot of things wrong with it. It even has things where people's email addresses changed. And so it has this mapping file. This comes along with it. This mapping file that says, here's this one person, and here are the 6 email addresses that they used throughout the life of the project. And so there is a relatively complex, and so this part here is super slow, very slow. This part here is slow, but it'll take, like, depending on how fast your computer is, somewhere between 2 minutes and 10 minutes. This first part will take days, perhaps, depending on the speed of your network connection. And so what Gmodel does is it reads through this. It actually recreates, it wipes this out and recreates index.sqlite every time it runs, so that you can change any number of things, you can respider things, you can do whatever. And often the cleanup, this is one of those cleanup processes, and you have to tweak the cleanup process. You like look at your data like, oh, the cleanup missed something, so I got to run it again. So this produces index.sqlite every time it runs. So this is like 2 to 10 minutes. Gmodel is 2 to 10 minutes. And it like maps names, and when it's all said and done, this is a very small, highly normalized, it's a nice data model. This one here had the Content SQLite has an ugly data model. Index.SQLite has a pretty data model. It's got foreign keys, it's got all this stuff, and all those things we talked about in the database where it's efficient. And so in your mind, keep track of how fast it is to scan all the data in a database with a bad model, and then watch when you run like GBasic, which is a scanner, or GLine, which produces line data, or GWord, and watch how fast they run. They run in like a couple of seconds at the most, and this runs in 2 to 10 minutes. And the difference is that's because the data is efficiently modeled in index.SQLite. So you can take a look at that using SQLite browser and take a look at the data model, and you'll see it looks just like the stuff we talked about in the database chapter. It's got foreign keys and all those things. And so that runs, and you got this, and then we do our visualizations and our analysis from this clean version of all the data. And so GBasic just loops through and prints some stuff out. It's a great way to test things. It's a pretty easy to understand program, and you could take a look at it. GLine does some bucketing and makes some histograms to produce a line graph. And then GWord does a different histogram. It does a histogram of word frequency and then produces that as the word frequency ends up in gword.js. And then we have 2 HTML files that use the d3.js visualization to produce a line and a word chart. And so, you know, in another video I will show you how this code works, which is probably more useful than this picture. But this is a whole bunch of good stuff in this particular application, and if you really understand everything in here, you can build a pretty sophisticated data retrieval and analysis pipeline. And so that's it. I thank you for watching all these lectures, and look forward to seeing you on the net. We're doing some code walkthroughs. If you want to get the source code, you can take a look at the sample code and download it and work through it. And so what we're working on now is doing some retrieval and visualization of email data. It's kind of ironic. We are going to now look at the email data that we that we started with. It's the same Sakai developer list email data. And so there's this service called Gmain. And Gmain archives developer lists and various email lists, and I've made a copy of their data because all the students in my class hitting their server with their API would crush it. So in order to be a nice guy, I put up a much more powerful server with just the data from this one list. And it's about a gigabyte of data, so be real careful if you're paying for network. So the basic process we're going to go through is we're going to have a spidering process that's a simple, restartable, focused on the network problems, data pulling to pull content.SQLite, and there's going to be a database there. And then we're going to have a cleanup process. This database is going to get large, about a gigabyte. And then we're going to have a process that kind of grinds through this data. It takes a while. And so then it's going to read this mapping, and I'll show you that when it comes, because things like people's names have changed over all these years. and it does a cleanup and makes a really nice, highly relational version of this data. And then we visualize from here. And so this could take you several days to finish this. This will take like a few minutes to run, and then this will just take seconds to run. And so this is a multi-step process where if you were doing something like running something for 2 days to produce